Hello and welcome once again to the first part of this course. I am Mrigank. In the introduction session, I gave you a brief overview, a hint of what we are going to cover in the first few lectures on analog design. So, it is going to be from the very essential characteristics of the devices that we are going to use in the circuits, using those devices in building fundamental building blocks of signal processing systems, doing the analysis of those circuits, including DC, AC, small signal analysis, frequency response, noise analysis, signal swing and linearity to some extent. And then once we are through these basic steps, once we have gone through the device concepts, their application in circuits and the tools, the basic steps required to analyze those circuits, then we can apply those concepts in building essential components of a mixed signal design, the analog front end. So, if I talk about analog front end, we can look at the whole system, as I said, as a shell where the analog front end acts like the outer covering or the thin shell which separates the bulky digital engine from the external world. So, the external world is providing us all kinds of analog signal which has to be processed, conditioned and provided to the digital domain with the help of this thin shell of analog front end. So, we are going to talk about the fundamentals required to understand the design of a practical system interfacing the real world signal to the digital world. So, what are the fundamental blocks that come into such a system? So, if I try to draw a generic analog front end, we may have a sensor which is giving us a real world data. The first stage happens to be amplification of that weak signal being provided by the sensor. The sensor itself may be having good amount of noise, or there can be additional noise coming from environment. We need to make sure that the first amplifier itself does not have noise or distortion getting introduced into the signal. So, the first stage must be low noise amplifier. Although this term of low noise amplifier is kind of preserved for RFIC low noise amplifier or LNA, where we have to deal with high frequency operation, matching consideration. But in general, in analog design also, whenever we are facing the analog signal or sensor to the mixed signal IC, the first stage happens to be the low noise amplifier, where apart from amplifying the signal, the amplifier must make sure that it is not corrupting the signal by added noise. So, this amplifier is going to have so many different components. It is going to have transistors, resistors, capacitors. Transistors and resistors, they can contribute to different noises and they can in fact corrupt the signal. So, we must make sure that the noise contributed by the first amplifier stage is significantly lower as compared to the signal over here. The noise level here, RMS value of the noise should be much weaker as compared to the peak to peak signal that is being received by the sensor. The next block happens to be a variable gain amplifier. We can denote it with an arrow. It means that the gain of this stage is variable or adjustable in order to amplify the signal further and also meet the dynamic range of the next processing blocks, which may be the filters and the ADC. So, we will discuss that why this requirement of variable gain amplifier is coming into picture when we go into the block level specifications and the designs. After the variable gain amplifier, we may have a frequency selective block in the form of a filter. In general, the filters perform one of the most essential block, that is anti-aliasing. Before the digital mixed signal part, ADC is sampling the signal and converting into discrete time. Apart from that, in many cases we may need to reject noises dominant in certain frequency ranges. So, noise rejection along with that anti-aliasing can be an important function of the filter. After the filter, we have the A to D converter, which is supposed to digitize the conditioned and the processed analog signal being received at its input. The signal over here is already processed, amplified, filtered, noises have been taken care of. The amplification over here is such that it is matching with the dynamic range of the ADC. So, in general ADC will have a certain dynamic range, it can process input signal from certain maximum value to certain minimum value. So, we have to make sure that the signal reaching at the input of the ADC, it is having a range matching with the maximum input range of the ADC. So, that we can take the maximum advantage of the dynamic range of the ADC. Now, the ADC specification also may heavily depend upon the kind of signal we are using, how many bit precision we need, what is the sampling rate and so on. It may depend upon the ADC's signal specifications. After the ADC, we may have signal processing going on in digital domain. We can denote it as a DSP block, where you are trying to do some local processing on the signal acquired through the sensor. You may be running a lot of complicated signal processing algorithm, their low power implementation in the DSP module. So, towards if we talk about today's scenario, when people are talking about very low power self sustained sensor nodes, for example, which are supposed to be operating with very low power battery based operation, maybe operated with energy harvesting, there the power budget of the entire system is going to be very limited. We are supposed to acquire real time signals from some sensors continuously and make sure that the signal integrity is maintained all the way to ADC while doing the analog domain processing. Following that, we need to transmit that acquired data through a wireless link to a central unit which has much more computation power, memory and resources, which is not so much power constrained. So, do that we may need some digital domain processing before we can send that data out, which helps in processing, compressing and extracting certain essential information out of the data coming from the ADC. And once we have the final data ready to be transmitted, we may have the RF IC block, which is supposed to wirelessly communicate the data to the central unit. So, in this course, of course, we are supposed to cover the three fundamental units. The very first one is of course the analog signal acquisition chain, which I will be covering in my lectures, that constitutes this entire signal chain of front end amplification, filtering and analog to digital conversion. Now, this course of course is supposed to start from undergrad level content, and based on the feedback that we have received in our earlier sessions, it has been recommended that we touch upon the fundamental issues related to devices and the basic building blocks, that is the circuits, which are going to be applied in building these blocks. So, we consider it very important to touch upon the fundamentals related with the device characteristics, because the kind of characteristics, the kind of information needed from device perspective is going to be very different in case of analog, and is going to be very different in case of a DSP or a digital block. So, some kind of device parameter that we are so much concerned about while doing the analog design, we may not be so concerned about them in the digital design, because there the device characteristics are different, the kind of region the device is operating it is different. So, it is important to be aware of the device characteristics, the large signal behavior, small signal behavior, noise, frequency response and so on. So, that while applying those devices in the circuit, we are confident about the circuit operation, we are able to understand its implications in the circuit's performance, maybe DC, maybe power consumption, frequency response and so many other important aspects. So, the starting point is going through the fundamentals of the basic building blocks. So, let me jot down what are the issues, what are the device level concepts we are going to cover in this course. So, if I talk about devices, it essentially means the CMOS technology. As we have introduced in the very beginning, CMOS is the key technology which has enabled extensive miniaturization, combination of analog and digital into mixed signal ICs, where both analog and digital can be sitting together. And because MOSFET has facilitated aggressive scaling, it has outperformed the previous devices in the form of BJT in terms of performance as well. Earlier technologies, BJT used to be a choice for analog front end or analog design, because it used to offer higher mobility or higher performance. But why MOSFET took over? Because it is a lateral structure, as compared to BJT, which is relatively having a vertical structure with 3 terminals, which is relatively more difficult to scale. As compared to that, MOSFET is a lateral or a relatively 2D structure, which has been much more convenient to scale, and industry has been very diligently following the Moore's law and has been able to scale the channel length of the MOSFET starting from earlier days of 1 micrometer going down all the way to 15 nanometer, and today they are progressing towards 10 and 7 nanometer. So, because of this aggressive scaling provided by the MOSFET technology, it has in many ways outperformed the MOSFET in terms of performance also. Therefore, the focus shifted completely towards MOSFET, and trying to integrate MOSFET based analog as well as digital design together in form of a mixed signal SOC has become the main focus of the industry. So, when we talk about devices, it will be mostly about the MOSFET device characteristics, which are essential to understand in order to apply them in analog mixed signal circuit design. So, while covering devices, the very first thing that we have to be clear about is the DC characteristics of the MOSFET, the IDVD characteristics, IDVGS characteristics, understanding the large signal behavior. Now, when we are talking about analog, when we are talking about processing those minute analog signals acquired from external world, we are essentially talking about small signal operations. So, we need to understand the physical characteristics of the device which enable that small signal operation. While we are doing digital operation, there the MOSFETs are being used as switches, right. So, either it is in on condition or in off condition. So, there we are not so much concerned about the physics of the device, about the physical characteristics of the device. We are not exploiting the physical characteristics of the device in doing the processing or the computation. But when it comes to analog processing, it is all about using the physical characteristics of the devices to enable small signal operation, to enable amplification, to enable signal processing, to enable filtering, to enable the frequency characteristics of the devices, to allow us certain frequency domain characteristics, likewise suppressing the noise characteristics of the devices, making sure that it is not corrupting the analog signal. So, the core physics of the device becomes a lot more important while dealing with analog circuits, and therefore, understanding the device, understanding the MOSFET from the point of view of analog design becomes very crucial before we take up any complicated, comprehensive block level or system level design like low noise amplifier or filters or ADC. And the same holds true for the RFIC. There are some more concepts related to higher frequency operation comes into picture, some additional parasitics need to be taken care of, some additional device modifications need to be incorporated, and the device may need to be optimized for RFIC operation in a slightly different way. But the fundamentals remain same. For applying MOSFETs in analog design or RF design, is very important that we are aware of the device characteristics which enable that analog or RF operation. So, next comes is your small signal operation and model. How do these DC characteristics of the devices enable small signal operation? So, once again, as we said, we have to look into the small signal behavior. How does the small signal model can be constructed out of the DC characteristics of the devices? How does it make sense? What do we mean by transconductance? What do we mean by the small signal output resistance of the MOSFET? What do we mean by channel length modulation? What do we mean by the noise component in the MOSFET? How do the parasitic capacitances come into picture? How do they depend upon the device dimension? If you are increasing the device dimension, how does the parasitic capacitances change? How do the small signal parameters like GM, RO change? If you change the DC bias condition, how do these small signal parameters change? So, that is very important to understand, because when we are talking about IC design, we have some parameters in our hand that we can adjust. So, while dealing with an IC design, while dealing with a real world mixed signal design, we have certain parameters at our disposal, and it is important to understand how to decide about the choice of these parameters, so that we can get to design our circuits meeting the required specs and get the best performance out of it. So, towards that end, the first point is understanding the small signal operation, not just the definition, not just the formulae, but the origin of those small signal parameters, how they are coming into picture and making real sense of it. So, the purpose should not be just remembering the formula and solving some numerical problems. It is very important, very crucial to have the physical intuition of the overall process. It is very important to see how the GM is coming. It is very important to see how the small signal resistance of the MOSFET is coming. Why does the drain give us high impedance? Why does the source give us low impedance, and so on. So, if we are having that physical characteristics of the device in our mind, we can very well understand and appreciate the application of those devices in analog circuits, because it does require having a very good grasp of the real physical operation of the device, large signal as well as small signal, to deal with the circuits efficiently. So, in connection with the small signal model, once again we are going to have a discussion on high frequency model, where we are going to talk about the parasitic capacitances, their origin, how do they influence the circuit operation, and so on. So, once again understanding the origin of parasitic capacitances is important, not just looking at the pictorial model of the parasitic capacitances, some parasitic connected between drain and gate and source, but it is also important to appreciate what is their origin. So, we are going to look into parasitic capacitances. And finally, one of the very important issues when we are dealing with practical design is the noise model. So, because of the current flow in these kind of nanoscale, microscale devices, we have several sources of noise. We will try to understand the origin of noise in the device, how to model it, how to include that effect in the small signal characteristics, so that we can apply that complete model, including small signal low frequency components, the high frequency parasitic capacitances, along with the equivalent noise sources in doing the analysis for the circuit, complete analysis for the circuit. Now, once we are gone through these device characteristics, we will be in a good position to look at the circuits and apply those device concepts in building our circuits. So, next comes the topic which we are going to cover while describing circuits. So, first is going to be a common source amplifier with active load. This is a very fundamental block, because once we are comfortable with the common source amplifier and the design steps associated with that, the signal analysis, DC characteristics, small signal analysis, frequency response and noise analysis associated with the common source amplifier, we will be in a good position to go towards more complicated circuits like differential amplifier, two-stage amplifier, op-amp and so on, which are going to be essentially our building blocks for building larger functional units like the low noise amplifier, filters, ADC and so on. So, this is the very first stage talking about the common source amplifier. How does it depend, how does the functionality depend upon the choice of load, and being comfortable with the fundamental steps in analyzing those circuits: DC, small signal, high frequency and the noise model. The next step is going to be differential amplifier with current mirror load and current source load. Now, once again, these two topologies of differential amplifiers are very fundamental and may be very crucial in designing different blocks that we are going to use in our low noise amplifier design. So, understanding these two basic topologies of the differential amplifier with current mirror load and current source load, how they are different, how do their DC biasing, frequency response, small signal differ, and while using them in a circuit, what are the practical design considerations that we need to make. It is very important to understand while proceeding towards our larger functional blocks. So, we will spend some time on understanding the differential amplifier, and this will also incorporate some discussion on current source that is related to the biasing scheme. How do we operate differential amplifier, what is the basic principle of differential amplifier operation and its connection with the next higher level, that is a two-stage amplifier or an op-amp. Now, this two-stage op-amp is going to be our building block for the first stage, that is our low noise amplifier as well as the variable gain amplifier. So, there once again we will need to understand the basic characteristics, the four basic analysis: DC, small signal, high frequency and the noise model, in order to be able to appreciate the design issues associated with the very first stage of our mixed signal front end, analog front end, that is the low noise amplifier and the variable gain amplifier. So, we will talk about many practical considerations. We will pick up an example, a particular case where we are building an analog front end for a biomedical signal and try to study the characteristics of the signal, and based on that signal we will be trying to determine what is the specs of the entire analog signal acquisition chain. From those specs we will try to figure out what is going to be the spec for the front end amplifier, and the front end amplifier specs will tell us something about the specification of this two-stage amplifier, which is going to be used in building that no noise amplifier. So, there is a top down approach. Highest level we are having the signal known that we are going to process, acquire and process. That gives us some specification about the system, about the entire signal acquisition chain. It is some way also linked with the digital processing. So, the DSP person may tell me that in order to process this algorithm he required certain resolution in the digital domain. Without that resolution he was not able to get accurate results in whatever signal processing is trying to do. So, there is definitely some feedback from the digital domain. I need to talk to the digital person, I need to talk to the DSP engineer who is telling me, who is giving me the specification of the bit resolution required for extracting more sophisticated, more hidden information from the signal, and I have to address that need, and that in a way has a feedback and tells me something about the specifications. So, first set of specifications come from the signal itself. What is the frequency content of the signal, what is the noise content of the signal, what is the amplitude of the signal, whether the signal is stationary, whether it is having some dynamic offset, whether the baseline is fluctuating. All those considerations define my front end design specs. But equally important is the feedback from the person doing the digital signal processing, because he is going to tell me how much resolution, how much linearity, how much precision and accuracy the analog block should preserve, so that the digital block can do more extensive computation in digital processing and extract the required information. So, there is always a feedback from the digital people also to design this or determine the specs of the entire analog signal acquisition chain. So, this is how we are going to detail the discussion on two-stage op-amp, and in order to do that we are going to require some additional concepts like feedback and stability, which is going to be very important while dealing with the design of a two-stage amplifier operating in feedback mode. So, we will have some discussion on feedback and stability, which is again linked to frequency response in a tight manner. Another topic that may be essential to cover at circuit level before we go towards the blocks is going to be switched capacitor circuits. Which basically deal with some special kinds of circuit techniques which can be very useful while dealing with practical analog front end design. It basically involves combination of MOSFET switches and capacitors integrated along with operational amplifiers to give us some interesting functionality for amplification purpose, for filtering purpose, A to D conversion and so on. So, the switched capacitor circuits are also going to be very fundamental in coming up to the higher level. They are going to be very much essential. They are going to act like a link between the whatever circuit level components we discussed and their application in building the functional units, namely the amplifiers, filters and the ADC. So, we will have some discussion on the switched capacitor circuit concepts as well. So, once we are done with the basic circuit analysis, then we are ready to go on towards the blocks, the building blocks of our front end system, that is the low noise amplifier, front end amplifier, filter and the ADC. So, amplifier part, as we have already said, we will be using the operational amplifier in conjunction with some switched capacitor units to arrive at the amplifier design. There will be some additional concepts required to address some practical issues. So, that we will be covering as we go on. Filters, once again we are talking about not just some breadboard circuits where we have large resistances and capacitances at our disposal that we can use to get a desired frequency response. While designing filters for integrated circuits, we are faced with certain stringent constraints. You cannot have any arbitrary value of R and C. For example, on breadboard circuits and PCB design, we can have arbitrary large C, millifarad, farad, microfarad, nanofarad. We have a very wide range of C and R through which we can design appropriate filters. But when we are talking about using on-chip components, the value of C and R that we can use to get a desired frequency characteristics is going to be very limited. A single millimeter square area chip cannot afford more than say a nanofarad of capacitance. So, total capacitance summed together in the entire 1 millimeter die can be limited to 1 nanofarad, and in general individual capacitances used in the circuits, for example, in 180 nanometer technology may be well within 100 picofarad. There will be very few which are around that range, most of them will be few picofarad or smaller. So, likewise for resistors also, we need to take care of the practical consideration, the constraints provided by the IC design environment, and appropriately choose the R and C component to meet our filter characteristics. Many other issues like the component variations, mismatches are going to play important role, are going to be it is going to be necessary to consider those while trying to arrive at a desired frequency characteristics of the filter, and that tells us about the kind of topology we are going to require to meet our specifications. A simple op-amp with R and C feedback may not be the best topology to use because we do not have those R and C values available. So, once again we may have to go for switched capacitor filters or GMC filters, where we are going to use active blocks, transconductance blocks similar to differential amplifiers, similar to operational transconductance amplifiers and op-amps that we are looking at in the earlier sections. So, we are going to look at two basic popular topologies, two popular schemes for implementing on-chip integrated filters for the kind of signal we are using here for biomedical signals. And we will see what are the advantages and disadvantages of these two schemes, and what are the circuit issues, how we can make a judicious choice between the two schemes, and then go towards the component and transistor level implementation of these two schemes. Finally, the ADC, which deals with the preprocessing, the digitization of the preprocessed analog signal and interfaces the processed analog signal with the digital world. That is again another very broad topic. Many different topologies, many different kinds of ADCs exist. Within a single topology, you may have many different variants, many different proposals for implementing that topology. So, as I said, the ADC itself can be a full 1 semester course, and still we may not be able to cover enough. It is a very broad topic. Likewise, of course, the same holds true for amplifiers and filters. You can have full semester courses just dealing with filters and amplifiers. But the objective of this course is to give you a taste. Pick up an example, pick up a case study. In this case, we are talking about biomedical signal. We have a certain frequency range of interest. We have a certain signal amplitude, signal characteristics in our mind, and we are going to choose an ADC topology which is suitable for that particular signal. So, we will talk about the basic definitions or specifications related to the ADC to begin with, basic definitions and specs of the ADC, and then we will choose a particular topology suitable for a biomedical signal processing device, which may be a SAR ADC, successive approximation ADC, which is inherently also having the DAC involved. So, that is a good point about it, because we can also very briefly have a discussion on the DAC part. So, possibly whatever we discuss in the switch capacitor circuits and to some extent in the earlier sections on differential amplifiers and op-amp, that is again going to be very useful while talking about the SAR ADC. So, all the design concepts that we talk about at the block level are going to depend heavily upon the fundamentals that we build, right, starting from the device characteristics, their application in circuits, analyzing those circuits, and then finally applying those circuits and building these blocks to meet our specs. So, to cover all this in a total of, I think I would say 6 classes, that is just 9 to 10 hours, is a challenging task definitely, while making sure that people having very weak link, very weak previous link with analog, they are also comfortable with the material covered. So, please feel free to post your comments if at any point you feel that we are taking a jump and we are skipping certain things that you are not aware of, or you would like to stop at a particular point and ask me to emphasize on certain aspects which have not been covered. Feel free to do that. You can post your comments online and I will be happy to respond to those, especially the broader comments which are being posted by a lot of people. So, it may be difficult for me to respond to all comments, because there are so many of us attending this session together, but definitely the broad and the more relatively repeated comments and the demands, I will try to cater to them definitely. So, this is the broad outline of what we are going to do in the analog front end part. And let me once again talk about the different kinds of applications that we can have in mind. So, for this course we have just chosen biomedical signal processing as an application. Likewise, when we are talking about today's industry's interest in IoT, Internet of Things, sensor nodes, where people are imagining all kinds of low power devices which can operate with battery without even replacing the battery for very long hours. They can be devices which can be fitted over bridge and buildings. They can sense the environmental conditions, they can sense the structural stability, vibrations coming in those buildings. Likewise, you can have devices which you are wearing on your body. So, in future we may see wearable devices where some of those chips can be implemented in your wearables, in your clothes, which are acquiring your biophysical signal and transmitting it to your handheld device like a cell phone. Even more exciting, there can be implantable devices which can go inside our body. They can go inside our brain and acquire some very critical health signals and transmit it outside. We can have devices which can acquire important signals from the brain and let us manipulate those signals or take help of those signals to do some interesting thing outside. So, biomedical engineering or application of these analog mixed signal design in biomedical engineering is a very exciting field with a lot of interesting research opportunities available worldwide, and therefore, just at a high level I have chosen this particular topic, signal characteristics aligned with biomedical application, to present this course. And of course, as a part of our research, as a part of our projects, we do work on all these different applications with very bright, very dedicated students, and probably towards the end we can give you some example of such applications at high level. So, this is the very first slide that I showed to you. It was regarding generic front end, what is the basic components in the front end. So, we may say that okay, this is the basic front end, and at the max what we have to do is adjust the specifications. So, why do we need to invest so much time in learning analog once the design is made, once the low noise amplifier or the variable gain amplifier, filters and ADC is known? Why do we need to keep redesigning it? Technology node, suppose it is fixed, we are not so eager to go for technologies lower than 15 nanometer. In fact, for biomedical applications, people are working with 180 nanometer technology because there the speed or the scaling may not have so much advantage. So, why we still may be interested, why do we think that this field is still exciting if this is a standard front end available and already designed and well understood? So, we will try to address those issues. What are the challenges, what are the different aspects that we need to address while dealing with different applications. So, first thing is signal characteristics. In this particular application, we are dealing with biomedical signal. There are many different kinds of biomedical signals which can be acquired with different kinds of sensors. So, there itself the characteristics of the front end, the kind of analog signal processing you can do, the kind of front end amplifier, filter, ADC you are going to have is going to be very different. It may not be as simple analog chain like this. You can have many different functionalities embedded into the analog chain itself. You can have some interaction between the DSP part and the analog part. The digital part may need to give some instruction to the analog part to tune it, to calibrate it, program it or configure it according to the desired input signal. So, there is a tight interaction between the analog part and the digital part. In today's age, it is not very practical to confine ourselves only with analog or only with digital part, because these two things are getting so tightly linked. There is always some help of the digital part in calibrating or assisting the analog part. Likewise, in many cases the analog part may come in to the rescue of the digital part. So, we will take certain examples where that kind of interface between the analog and digital is being used. Digital part is assisting analog in a certain fashion, so that its performance, characteristics, specs can be improved. So, with that we would like to start with the basic core content, starting from the devices and going all the way to circuits and the blocks. So, as we said, the fundamental device which has facilitated proliferation of this technology is the MOSFET, metal oxide semiconductor field effect transistor. And we are all familiar with the basic current equations. Of course, we cannot go too deep into physics. We are just going to start from the current equations and from there go towards the large signal and small signal characteristics. So, this is the basic structure of a MOSFET. For N MOSFET, you may have a P type substrate that you start with. On the top of that, you are having a thin gate oxide created. So, you have an oxide layer SiO2. The reason why silicon has been so popular and not germanium is because Si has a native oxide which is very well matched with the silicon. So, the interface between the SiO2 and the silicon happens to be of high quality. That is one of the reasons why silicon has been the winner despite germanium having higher mobility. Because the moment you have poor oxide interface with the silicon, it can degrade the transistor characteristics, it can make it more noisy. So, it is very important to have this interface between the oxide and the silicon high quality. And then on the top of that you can have a metal or a polysilicon gate, which is forming the gate terminal. For forming the source and the drain, we have highly doped N plus regions, and once again, in order to have contact with the body terminal, we can have a P plus contact over here, highly doped P plus region, which is needed to lower the contact resistance associated with the body contact. So, this P plus acts like the body terminal. So, here I can name it as the B or the body terminal for the MOSFET. For an N well technology, we know what is the condition. We have this entire silicon wafer doped P type. So, this entire silicon wafer to begin with is doped P type, and the NMOS transistors, they are directly fabricated on the top of that silicon wafer. You have the N plus region and the gate forming the NMOS transistor directly on the P type substrate. In order to fabricate PMOS, on the other hand, we need N substrate and P channel, right. So, in order to get an M substrate, we create a well, an N type well within the P type doped substrate, where you have larger N doping. So, we are making this well region N type, and within this N type well we can create our P MOSFET. So, we can have the P plus regions for the source and the drain of the MOSFET. You can have the gate terminal and likewise the source and the drain terminal. And once again, in order to have the contact with the substrate of the N well, that is the body of the PMOS, we may need N plus contact over here. So, this is the body of the PMOS. So, this is the N well technology, where the substrate is P type. You are having all the NMOS transistors sharing the same substrate, because this P substrate to begin with is common to all the NMOS that you are directly fabricating on the P type substrate. Whereas, for NMOS we can have isolated wells. So, these are isolated regions which are which means that essentially different PMOS transistors, they can have different bulk contacts. So, each PMOS transistor can have a separate well, or you can have a larger well combining a lot of PMOS transistors used in a particular circuit. So, we need to be aware of this N well process, which is one of the most popular ones. There are many different tastes. You can have a P well process, you can have a dual well, triple well process, you can have silicon on insulator, where you can have PMOS as well as NMOS in separate wells sitting on insulator, and so on. So, there are different tastes, but commonly used a very popular one is N well technology, and we should be careful, we should be aware of the terminal characteristics of the substrate required for NMOS and PMOS, so that while talking about the real circuit design, we are aware of the body terminal, how to connect it, what is the effect if we are having different voltages at the body terminal. So, that also becomes important while looking at the circuits. So, now if I talk about the current equations, so most of us are familiar with the MOSFET current equations for different region of operation. For triode region, we can write down the current as VGS minus VT times VDS minus VDS square by 2. So, this is the triode region or linear region operation, where the dependency on the drain to source voltage is very strong, right. If the drain to source voltage is small, the current will be small. So, in this region we have a very strong dependency on VDS. So, if I plot ID versus VDS characteristics for this region, as the VDS increases, the current strongly increases with the applied voltage. and these are the curves for different values of Vg. So, we are plotting for different values of Vg, the curves will be going higher. So, this is called the linear region or triode region operation of the device, because here the device is having 3 terminal operation, a strong 3 terminal operation, it is acting like a triode. So, the name is borrowed from a diode, where you have essentially 2 terminal operations, right. In a diode we have 2 terminals, you can control the voltage across those 2 terminals, and that is going to control the current flow across that 2 terminal device. So, it is a diode. In the triode region, the current flow through this MOSFET, assuming that the body terminal is fixed or it is at a particular potential. So, we are going to fix the body terminal for the time being and mainly concentrate on the other 3 terminals, that is the gate, drain and the source. So, assuming that body terminal is at a fixed point, here in the triode region, if you are applying a certain gate to source voltage, call it VGS, and then applying a particular drain to source voltage, call it VDS, the resultant drain current is strongly dependent upon both the voltages, gate to source as well as drain to source. Therefore, the current through the MOSFET is being controlled by 3 terminals, and therefore, we can say it is a triode region operation of the device. And we will see why this operation is not commonly used for amplification purposes. For building analog circuits, we need saturation region operation. So, we will see how to use saturation region operation, why saturation region operation is necessary, and how to employ that in building our circuits. So, what is the fundamental reason why we are going for saturation region operation? So, for saturation region, we know what is the overall current equation. The first term gives us the square dependency of current on the gate to source voltage, VGS minus VT square, and the second term gives us dependency on the drain to source voltage, the proportionality factor being lambda. So, we will briefly discuss this concept of lambda and how does the channel length modulation occur and what is its role in analog circuits. It plays a very important role in analog circuits. Channel length modulation or lambda, it is crucial to understand what is its implications on the large signal and small signal operation of the MOSFET, and how do we exploit it in building high gain amplifiers. So, this is a very important factor which we may not worry about while designing digital circuits, because in digital circuits most of the time transistors may be in this region, in deep triode region. We are not so much concerned about the channel length modulation, we are not so much concerned about lambda. So, here we do need to understand the effect of lambda, its DC characteristics as well as its effect on the small signal characteristics and the small signal model. We may at some point need the sub threshold, sub VT or sub threshold characteristics of the MOSFET, which is having an exponential relationship or exponential dependency on the gate to source as well as drain to source voltages. So, generally when we are talking about very low power circuits, sub threshold operation is critical, where to save powers we are lowering down the supply voltages. So, the concept of power dissipation comes in a big way, whether we are talking about analog design or digital design, mixed signal design for a power constrained environment, say a sensor node or a biomedical application, where the overall power budget may be very limited. And in those conditions, we would like to aggressively scale down the supply voltages, and it can be even lower than or close to the threshold voltage of the device. And in that case, definitely the transistors are operating in deep sub threshold regime. We cannot apply the square law of the MOSFET directly and from there derive the small signal parameters. Rather, we need to use the sub VT equations of the MOSFET, which again can be derived rigorously through device physics, but we are going to definitely avoid those parts. We are going to use the equations and try to see how does the same small signal parameter that we are arriving at using the saturation region operation gets modified when we use the sub threshold region operation having exponential dependency on the terminal characteristics, terminal voltages. So, for a sub threshold operation of the MOSFET, we have exponential dependency on the gate to source voltage, and there is a non-ideality factor m over here. VTH is the threshold voltage, and also there is a weak dependency on drain to source voltage. K is the Boltzmann constant, Kt by Q. Kt by Q at room temperature is around 25 millivolt. So, if VDS is sufficiently larger than Kt by Q, that is around 25 millivolt at room temperature, we can approximate this current as just the first term again ignore the second term, because for larger VDS, more positive VDS, the second term almost becomes negligible as compared to 1. So, we can drop it and we can just use the first term over here to find out the small signal parameter. So, this becomes our DC current equation, and from here we can try to find out the small signal parameters of the MOSFET. Once again, in order to find out this, the concept of output impedance, we may again need to take care of the second term. So, that is going to come into picture at some point. So, towards the end, when we are talking about low power front end amplifier design, we may just revisit this concept of subthreshold operation and define our parameters parallelly in terms of subthreshold operation, so that in case some of you in future are working on very low power circuits, subthreshold circuits, you can or teaching these similar topics, we can explain this operation mode as well. Thanks a lot.